So today's lecture we will continue on Fourier transform. So Friday lecture there was the other instructor who started the Fourier transform, and now we'll continue on it. So today is Monday, and the readings from page 218 to 222. And it's also the due date for MATLAB projects, so I assume everyone should submit their projects. Then, in Wednesday, actually there will be no class. Okay? So the reason we are observing a holiday is called Eid al-Fitr, which is basically breaking the fast holiday, so I will not be able to be here. Then our next meeting will be Friday. Then ratings from page 223 to 213. Then next week, on Monday, the readings from page 261 to 263. And it's the due date for homework number 13. So some important tables related to Fourier transform, which are table 5.6 and table 5.7. So you will see something similar to when we discussed Laplace transformation, two tables, two important tables, and the same thing for Fourier transform. Okay? So in summary, what we expect to see for the rest of this course, this week and next week, Fourier transform. Then there will be exam. When is the exam? The 22nd. Okay, which will be not next week, the week after next week, which is Monday. So we expect by the end of next week to finish Fourier transform. Then in the exam will be based on Fourier series and Fourier transform. That's the third exam. After the exam, there will be a couple of lectures. These two lectures will be based on polyglots. So these two, or this topic will be then the final. Will be the final. So the final will equal the first exam, second exam, third exam, in addition to the polyglots. So polyglots will not be in the third exam, but it will be in the final. Okay, that's the plan. So again, Fourier series, finish up Fourier transform this next week. Then polyglot after the third exam. So the third exam will be Fourier transform and Fourier series. Any questions? Okay. Now a quick recap. When should I use Fourier series? When should I use Fourier transform? What do you think? Fourier series when it's periodic, Fourier transform for non-periodic signal or geometric signal. That's it. So Fourier series shortcut has Fs, whereas Fourier transform as Ft. So this one for Fourier series for periodic signal, while Fourier transform it's for general signal. The equation that we use for Fourier series, let's assume the equation which is the exponential term. X of t equal the sum when k equal negative infinity to infinity, x sub k e power j k omega naught t. How to find xk? Xk will be Fourier coefficient, which is 1 over t, the integral from negative t over 2 until t over 2, x of t e power negative j k omega naught t. That's what we did in the exponential term. And most likely, in Fourier series, when we did the analysis later, the exponential term will be the most commonly used. Then the general expression for Fourier transform, as it's been discussed last lecture, x of t will be 1 over 2 pi, the integral from negative infinity to infinity, x of omega, and keep in mind x will be uppercase, e power j omega t, then d omega. Keep in mind it's e omega, not dt. And x will be uppercase as well. How to find our, or if we need to calculate x of omega, which is basically the integral from negative infinity to infinity, x of t, e power negative j omega t dt. So keep in mind dt. So in Fourier series, Fourier transform, basically we will convert the signal from time domain to frequency domain. Okay? So it will be very similar to Laplace transformation. Laplace transformation will convert time domain to S domain, but here we will convert this to frequency domain. So now there are similarities between Fourier series and Laplace transform. Fourier transform, I'm sorry, and Laplace transform. Laplace transform versus Fourier transform. So in Laplace transform, we used to say Laplace of x of t, which is x of s, and x of s is actually the integral from 0 negative to infinity, x of t e power negative st dt. That was Laplace. While in Fourier, we will say like the Fourier transform, something like this, simple triangle like this, f as x of t, then it will be as x uppercase of omega. So in this series Fourier Laplace, we used to say x of s, x as of uppercase. Here we will use x of omega. Okay? Then how to find x of omega? It will be the integral from negative infinity to infinity, keep in mind negative infinity to infinity, x of t, e power negative j omega t dt. Okay? So you will notice they are very similar to each other. Fourier series, Fourier transform, Laplace transform, they are very similar. Or I would say Fourier transform is a special case of Laplace transform. How? We know in Laplace transform the S operator. S operator can be complex number. We call the S plane, which is sigma plus j omega. Here is sigma, here is j omega, right? So if we assume sigma 0, this yields S to be j omega. Okay? So instead of saying x of s, it will be as x of j omega, or in other words, we used to say x of omega. Then this is what's Fourier transform. So I would say, if you assume sigma equal to 0, then it is Fourier transform. So in other words, Fourier transform is a special case of Laplace transform. Okay? In summary, the signals can be, if it's periodic, we will use Fourier series. If it's not periodic, you can use Fourier transform or Laplace transform. Which one do you use? Depending on what you need. If you have sigma equal to 0, or which is S operator with sigma equal to 0, then you can use only Fourier transform. Okay, so I can say, assume we have S sigma plus j omega. So if sigma equals 0, this equals S equal to j omega, which means we are in imaginary axis. So when we do the plots, here is sigma, here is j omega, then our working area here, which is especially because we only have the imaginary axis. And we need to make sure also x of t is causal. If these two conditions, number one, sigma equal to 0 and x of t is causal, then we can say, so if 1 and 2 meets, then we can say x of t, or if not, then x of omega, which is Fourier transform, is a special case of Laplace transform. Okay? we have 1 and 2, which is the first thing. We need to make sure it's causal, and in real life all the systems are causal. Then the second thing, which is keep in mind the sigma or real parts will be 0. Now there is something is called the convergence region of Laplace transform. So we can say there exists a sigma 0, a value sigma 0 such that Laplace transform exists for all s with real part of s larger than sigma 0. What do I mean by this? We can say if we do the s-plane, which is sigma j omega, there should be a value, it's called sigma 0, this value. Then all of the poles, all of the poles will be within this area. So I will say all of the poles will be here. In other words, sigma 0 is non-infinity. So what does sigma 0 mean? Sigma 0 is the maximum real parts of all poles. Okay, let's imagine this example. Assume we have x of s equal to s plus 1 divided by s plus 2, s plus 3 minus j, s plus 3 plus j. So the poles here are s equal negative 2, s equal negative 3 plus j, s equal negative 3 minus j. Look at the real parts. The real parts, negative 2, negative 3, negative 3. What's the maximum real parts? Which is negative 2, right? Then when we plot this, here is negative 2, and here is negative 3, then we have ij, negative j. These are the poles. Then at negative 1, there is a 0. Okay, then what else? The axis is sigma, is j. So we can say the maximum is at negative 2, then the convergence region is this. Okay? Let's consider as convergence region. So, I would say that if this condition, x of t is causal, the other thing, the poles of x of s are on the left half plane thing, which means left half side, left hand side, left half side, left half plane. And you know what does left half plane would be? When we do the axis, this is left half plane. All of the poles at the left. In other words, we guarantee it's stable system. Then what will happen? Two results. The first result, which is x of s is convergent on the imaginary axis, and the other thing, Fourier transform of x of t will equal to Laplace transform, but substitute s equal j. So, as a result, I can use Laplace transform, just substitute s equal j omega, that's it. then I don't need to use extra tables. Or I can use it. I don't have to do Laplace transform, then it will be a special case. So this is a nice result, nice feature that sometimes if you do your analysis, you can rely on Fourier transform. You already know how to do it. They just substitute as equal to omega. But we need to make sure it is convergence on the imaginary axis. So again, in the previous example here, I just want to show you, I said the convergence region is after the -2, the largest pole. Then you can see the imaginary axis, this one, is within the convergence region. If it is within the convergence region, then we can consider Fourier transform equal to Laplace transform or substitutes as equal to 0. Okay? This is a special case. So the overall wide image is Laplace transform. Then Fourier transform is a special case of Laplace. So for this course, most likely we'll assume it's closed system. We will assume if it is stable system, then we can do this results. We can find Fourier series, Fourier Laplace transform, and we will find it using that. Any question? Now let me go for some examples, then try to do some analysis. Basically, I'm going to try to find Fourier transform using the general formula, the general equation, then I'm going to compare it in what we see this in Laplace transform to see, yes, is this one substitute as equal to omega, is this true? Yes, it should be true. So this nice results is very important for you. Let's go on example. Example. Assume x of t equal delta of t. Find x of omega. We can go to the table 5.2. It's 5.45. Table 5.6 and 5.7. We can use this table, but here I'm going to just try to prove it to say how we can find it in the equation. So according to the equation, x of omega equals the integral from negative delta infinity to infinity delta of t e power j omega t dt. Now, do you know how to find the integral of delta? Recall when we did exam number 1, sampling property. When we discussed about the delta function, we said when we have the integral from negative infinity to infinity f of t delta of t minus tau d tau, this is equal to f of tau. Or when we say the integral from negative infinity to infinity f of t delta of t dt and d tau, this is equal to, yes, dt equal to f of 0. Now, we don't have a phase shift, it's delta of t. So, according to the sampling property, it will be e power j omega t is a negative, then substitute when t equal to 0. Okay, does this make sense? We know this from the properties of delta function. If you have a problem on that, please go back to the delta function. You can go back to the recording, you can watch the recording, you can go back to the terminal system. So it will be e power negative 0, e power 0 equal to 1. Okay? So, as a result, we can say delta of t, when we convert this to omega domain, it will be 1. Okay, how about if we have x of t, here number 2, equal delta of t minus tau. How to find x of omega? X of omega, the integral from negative infinity to infinity, delta of t minus tau equal negative j omega t dt, which will make it substitute t equal tau equal negative j omega tau, which is the shift property. Okay? That's how we find x of t, x of tau when we convert this into x of omega. So let's compare. When we did, here is x of t, here is x of omega, this is Fourier transform. Here is Laplace transform, which is x of s. So when we did x of t will be like this. When we did the delta of t, we said it will be 1 in Fourier transform. In Fourier series, we said it will be 1 as well. In Laplace transform, we said it will be 1. So Laplace transform and Fourier transform are the same, because s equal to j omega, here there is no s, then 1, 1. No problem with that. Then, when we have delta of t minus tau, here in Fourier transform we found the e power negative j omega tau. However, in Fourier Laplace transform, it was e power negative s tau. So basically, you can substitute s equal to j omega, then we will get this. Just substitute s equal to j omega. Okay? Does this make sense? So now it's getting easy. Now Fourier series or Fourier transform is easy. Basically, just substitute s equal to j omega in that sense. Okay, let's do another example. Find Fourier transform of e power negative 18 u of t. Okay? So there are different ways. You can find it by going to the table, or you can find it by going using Laplace transform table or Fourier transform table, or you can go to Laplace transform, substitute s equal j omega. But here I'm going to just try to prove it using the equation, which is the integral. Let's use the integral. So here x of omega equal the integral from negative infinity to infinity e power negative 18 u of t e power negative j omega t dt. Now, since we have u of t, we can change the integral, because u of t, it will be 0, negative infinity to 0 will be 0, then from 0 to infinity will be 1. So we can say it will be from negative infinity to 0 will be 0, plus the integral from 0 to the infinity e power negative 80 u of t will be 1 equal negative j omega t dt. Okay, does this make sense? We just make it from 0 to infinity now. After that, since it's function of time, then we can say from negative infinity, so from 0 to infinity, e, take the e and t as a factor, it will be negative a plus j omega t. That's what we got, dt. Then the integral of the exponential will be 1 over, what's inside the power of the exponential? A plus j omega. Then exponential itself, e power negative a plus j omega t, then substitute when 0 and infinity. Okay, so we will say it will be as negative 1 over a plus j omega e power negative a plus j omega infinity times infinity, then minus e power negative a plus j omega times 0. Okay. So e power infinity, how will it be? E power negative a plus j omega t times infinity. That's the concern, to see how the value. Here, this one, e power negative 0, which is basically equal to 1. Right? So this term equal to 1. Now I need to know what's this term. How to calculate this term? I'm gonna try to put here e power negative a plus j omega t. Okay, then it will be as according to all the from e power negative 18 times e power negative j omega t. I can apply Euler's formula, which is going to be e power negative 18 cosine negative omega t plus e power negative at sine negative omega t, j sine. Okay? You know, e power j theta equals sine theta, or cosine theta plus j sine theta. Now let's substitute infinity, which is going to be e power negative infinity, cosine of infinity, plus j e power negative infinity, sine of infinity. Okay? So cosine infinity or sine infinity, this will be bounded between -1 to 1. Right? We know the sine or cosine will be between -1 to 1. But the concern is e power negative infinity. How will it be? Here is e power negative infinity. Negative infinity. So when it goes to this expression, at negative infinity will be 0. Right? So this yields to be 0 plus j0, or in other words, will be 0. So we will say that term is 0. Substitute this here. It is 0. So let me continue the analysis. So it will be -1 over a plus j omega times 0 minus 1. So -1 and 1. -1, the negative sign will be removed. It will be 1 over a plus j omega. Okay? Now, as a result, we can say, here is x of t. Here is x of omega, and here is x of s. X of t was e power negative at u of t. X of omega, it is 1 over a plus j omega. X of s, it is 1 over s plus a. Try to substitute s equal j omega, then yields this. Okay? So Fourier transform of x of t equal x of s, substitute when s equal to j omega. So that's, I would say, like method number 2. So we can say 1 over s plus a, substitute when s equal to j omega, and it will be 1 over j omega plus a, or a plus j omega, whatever. That's another way. Any question? So you see that for all concepts, it's not too difficult. So it's even easier than this Fourier series. We know how to do all plus transform. Then you have one choice: substitute s equal to j omega, or you can use the overall expression, or you can use the tables, whatever more convenient for you. Unless, and you see the question or the problem, use this method, use the integral method, or use the table, or use whatever. If you have the choice, choose the more convenient one for you. If you're not being told that use this method, use the method that's more convenient, then it should be fine. There it is, I think, a MATLAB code here in how to do to plot the Fourier transform for the symbol. So basically, this is the exponential form that we wrote here. This is decaying rates. When you find the variables, this is x1, and we see x, which is the Fourier series, Fourier transform, sorry, which is we say 1 over p plus j omega. That's what we did from calculate. Then we since we're gonna do the plots, we put them inside the vector, so it will be 0 and step 0.1 until 50. If you need more accuracy, you can increase the step size from 0.1 to 0.01 and so on. And here we draw it until 50, depending on the range, so you can increase it to 100, decrease it, it's up to you. Then x, it is a complex number. So how can I plot a complex number? When you have a complex number, you will plot the magnitudes alone, plot the angle alone. So there will be one plot for the magnitudes, one plot for the angle. Later, when we discuss the body plots, most likely we will do the natural algorithm for the magnitude and keep the angle. So anyway, we will discuss this later. But here we have the magnitude and the angle. So we will find the magnitude, which is the absolute value of the complex number, and the angle, which is we'll take the angle and keep in mind the default for the MATLAB is the angle in radian. So that's why I multiply by 180 divided by pi, because to convert the radian to degrees. Okay? Then the angle is omega, therefore it will be most likely radian per second. So it will not be frequency. But here just a point, convert this to, or we can convert it to degrees or convert it to radian. Then the other thing, when you see the products or the division, you will see these dots, and you will see these dots. These dots are in purpose. Why? Because we defined omega as a vector. So you can either make it inside a for loop, there's no need for the dots, then like put it inside a for loop, or you can make them as a dot or as a vector. So we define omega as a vector. Then dots means the product or the division will be elements by elements. This is in MATLAB problem. So we need to do element 1 divided by element 1. Then the other vector of element 2 divided by vector of element 2. The other will be element 3 and element 3. So it will make it element by element. If you didn't put this, then this will lead to some different things, which is if you can, I'm not sure if you're familiar with algebra, linear algebra. Then maybe you will go to the matrices and the dimensions. So when you do the product for the dimensions, for different dimensions, there will be this will need some error. So when we do dots here with adjective product with the product sign or the division, this means element by element. That's the point. So we will not use the product of the vectors or the division of the vectors. Then when we plot this yields, this is the magnitude. And we can label, X label, Y label. This is the magnitude with plots, and this is the angle plots. Again, later we will make this more advanced by using body plots. Okay? These are the angles. Now, let's do more the Fourier transform, which is, let's take as an example, the rectangular pulse. Fourier transform for rectangular pulse. Recall the last example, I think in Fourier series, we used rectangular, but we used that as a rectangular pulse train, which means that's repetitive pulse every specific period of time. That was the last example of Fourier series. But here, we're going to assume only as a single pulse. And this is common a lot in real life when you, it looks like when you press a push button. When you press a push button, it will be on when you press it, when you hold it, or when you remove your finger, it will be off. So even if you press it for quick, it will last for a few milliseconds, right? You cannot do it as impulse, as one signal at once. So when you press any push button, it will produce an impulse, right? Oh, sorry, and pulse, called a rectangular pulse. So the rectangular pulse, basically, we will assume this event happens once. There is no one keep pressing. Just you press it once, and we will see how this will affect. Here is t, here is x of t, then it will be between tau over 2, negative tau over 2, okay? And the amplitude is A. Here there's no period. You don't need to worry about t period, like t or negative t. These things does not exist, because this event happens once. So don't worry about the period t. It's not like, again, it's not pulse train. This event happens once. So there is no need to write t or other t. That event happens from t negative 2, from t tau over 2 until tau over 2. So how can we represent this into a time domain? Let's recall we discussed our first time. How do we represent this? We said we can represent this as a step function, which is x of t equal a u of t plus tau over 2 minus u of t minus tau over 2. Is this correct? So here is on time, here is off time. When t equal u of tau over 2 of when t equal tau over 2. We already discussed this. Or, do you remember the rect function? It can be a rect of t over tau. Basically, we will say that the pulse width equal to t over tau minus negative t over tau, which minus tau over 2. This will make it tau. The width tau. Then center at t equals 0. The center at t equals 0. Then we can say the rect of t minus center over the width. This yields rect of t minus 0 of tau. That's how we wrote this function. We already discussed this previously. Okay, just recall so you can remember this. Then this yields to be rect t over tau. So no matter if we wrote it as rect, if we wrote it as step function, it can be fine. Or you can write it as any equation, like a when negative tau over 2, t tau over 2, and 0 otherwise. Whatever. Okay? That's how we convert this time waveform into a time domain expression. So we just need to make sure that we know how to convert this into a time domain expression. Now, let's find Laplace transform, or actually Fourier transform. So x of omega equals to the integral from negative infinity to infinity x of t e power negative j omega t dt. So how we can find this? Basically, it will be the integral from 0 or from negative infinity until negative tau over 2 of 0 dt plus the integral from negative tau over 2 until tau over 2 of x of t here equal to a e power negative j omega t dt plus the integral from tau over 2 until infinity of 0 dt. Why I make it like this? You can put 0 otherwise, or it will be between negative tau over 2. Because the impulse happens only between negative tau over 2 until tau over 2. So as a result, it will be as the integral from negative tau over 2 until tau over 2 a e power negative j omega t dt, and this is the integral of an exponential, so it will be a over the power which is negative j omega, then e power negative j omega t substituted with negative tau over 2 tau over 2. So substitute it. It will be a over negative j omega e power negative j omega tau over 2 minus e power j omega tau over 2. Now, I need to convert this into, to do more simplifications, because again we need to, whenever we have e power j, we need to convert this to sine and cosine. That's the rule. We don't want to keep it as equal. If it is e power real number, okay, we'll stop here. But since it's e power negative j or e power positive j, whatever, we need to find a way to convert this into sine or cosine. We will do this every time. If it is in time domain, phasor domain, let's try to get rid of this. So how to get rid of this? Let's put negative j on the other side. So EA over omega. So what I'm gonna do negative, I will swap. I will substitute the negative here. So basically, L will be E negative E power negative j omega t over 2 plus E power j omega tau over 2 divided by j. And I can multiply by 2 over 2 as well. So this yields to me A over, or 2A over omega. Then I'm gonna flip to reduce, so to make it as E power j omega tau over 2 minus E power negative j omega tau over 2 divided by 2j. Then this is actually equivalent to what? This is equivalent to sine. Because sine e power j theta. Sine theta equal e power j theta minus e power negative j theta divided by 2j. Then this yields to be 2a over omega sine omega tau divided by 2. Okay? Now I can simplify it more. Let me try simplifying more. How? We can say, let's multiply this part by tau over delta. So this yields to be like this way. It will be A tau times 2 over omega tau sine omega tau over 2. Right? Now I'm going to put this here. So this yields to be A tau sine omega tau divided by 2 divided by omega tau divided by 2. Okay? And recall the sink. Sink x or sine x over x equal to sink. So as a result, it will be as A tau sink of omega tau divided by 2. Okay, this is x over x. And this is the pulse. This is the pulse, the rectangular pulse. Okay? Let's just make the plots. Here is t, here is x of t. And here is the pulse. This is area, negative tau over 2, tau over 2. Then here is x of omega, here is omega. It will be as start near tau, then it will be sine. Like this one. Okay? Then look at A tau here and look at the area of this one. So we can say quick notes that this is the area of this one. So the magnitude of the sink is the area of the time function. This is how easy. Maybe we'll use it later if the course is by here, just like a quick observation that the magnitude of the sink is the same as the area of the pulse. If it is more width, or the magnitude is more width, then the magnitude, the amplitude, the highest amplitude of the sink function will be depending on the area. Any question? Here is the MATLAB code for that one. So basically, recall in the MATLAB, the sink function is based on sine pi x pi over pi. But here we will use the unnormalized, which is our own function, sine x over x. Then we can, like, here's the MATLAB code. Then by comparing this is the time domain, and here's x of t. Here's x of omega, the same function. then we can see that the area here, which is here 2, the width here is 1. 1 times 2 will be 2. Then that's why the magnetic is 2 here. That's the first observation. The other thing, which is when we use, if we use the normalized, it will be 0, 1, 2, 4, 6, 8. If we use the unnormalized, then it will be as 0, 2 pi, 4 pi, etc. So the cross-section areas will be integers. 1, 2, here is 3, here is 4, here is 5, etc. And the same thing for the middle side. Now some observation about x of 0. Meaning of x of 0. Let's recall when I said here x of omega equal 8 tau sine omega t. Recall when I say x of omega equal to 8 tau sine of j or sine of omega omega tau. And we said this is the area of x. So if we substitute omega equals 0, what will happen? X of omega equal to 8 tau, because sine of 0 will be 1. Sine of 0 will be 1, which will make it 8 tau. So x of 0 will be 1, which is the same thing, which is area of x of 2. Now the question is this valid only for direct or valid for any elements? That's the question. Is this only valid for this example, or is this valid for any Fourier transform? How we can know that? Basically, we will say that x of omega equal to the integral from negative infinity to infinity x of t e power negative j omega t dt. Now when omega equals 0, let's substitute x of 0. X of 0 will be the integral from negative infinity to infinity x of t e power negative j 0 t dt. E power negative 0, e power 0 will be 1. So it will be the integral from negative infinity to infinity x of t dt. And the integral is 1. Oh, I'm sorry, the integral actually from negative infinity to infinity of dt, it's actually the area of x of t. Which is the same as x of 0. That's the nice result. How we can validate this? Basically, you can imagine this. Let's assume you have this function. And you have, for example, negative tau over 2 and tau over 2. So, x of 0 is the area. X of 1, while this one is x. Then the same thing if you have like any function like this. Here is x of t. Then if you find the area, this is x of 0. So as a result, x of 0 is the area for all of the elements. Okay? You understand now?